Over here in this animation, we can clearly see that the boy is rotating the stone continuously, and as we have earlier studied, the direction is continuously changing, because as and when it is rotating at different instants of time, the direction of motion of the stone that is attached to the string is constantly changing. So what is happening as a result? As a result, since direction is changing continuously, velocity is changing at every instant. Now, when velocity is changing with time, what can we say? That there is an acceleration that is present, because acceleration represented by A is nothing but velocity per unit time. So if the velocity is constantly changing, then obviously there has to be some sort of an acceleration present. Thus we can say that the stone accelerates. Now we have learned from Newton's second law of motion that force is directly proportional to two things. That is, force is directly proportional to m, mass, and it is directly proportional to acceleration. So when we see that there is an acceleration that is present on the stone, it means that there must be some sort of a force that is also acting on the stone. Thus, we conclude that because the stone is accelerating, there is a certain force that acts on the stone. So what is this force and how is it acting on the stone? Let us quickly find out. So in order to demonstrate this, we perform a very simple activity. Rotating the stone in the previous manner which I described, cut the stone. That is, cut the string through which the stone is rotating. Now you will find that while you are rotating the stone with the help of the string, the moment you cut the string, this stone flies off in a particular direction. So while rotating, while the string is cut, the stone no longer continues rotating. In other words, it flies off in a particular direction. So now let us analyze in which direction it is flying off. If you look at this closely, you will find that the stone is flying off after cutting the string in a direction that is tangential to the circular path. So now let us analyze this further. Over here, we find that the stone is rotating along this circular path. That is this path. Now let's say when the stone is over here, the stone is somewhere over here at one point of time, its direction of motion is in this direction. Now obviously, as you can see, if the string is held tightly, the stone is not going in this direction. It is not traveling in this direction despite the fact that its direction of motion is tending towards this particular side. Instead, what is happening? The direction of the stone changes and it comes in this direction. So at the next instant, let's say the stone is present over here. Again, over here, the stone has this particular direction. But even then, the stone is not moving off in this direction. Instead, what is happening? It comes over here and let's say it is present at this particular point. So this keeps on happening at all points along the circular motion of the stone. Now obviously, if we cut the string at any such instant, that particular stone will fly off in the direction at which it was tending to move at that point of time in the absence of the string. So if the string is cut off over here, then the stone will fly off in the tangential direction. Now consider something. I told you that if the stone is over here, it tends to go in this direction. But due to the presence of the string, it does not. Instead, it comes to this position. Similarly, from here, the tendency of motion is in this direction, but it does not move there, right? It moves here instead. Let us say we consider another direction for clear understanding. Let's say I have considered the stone in this position. Now over here, the stone is rotating in this direction. So the tendency of the stone, that is, the tendency of motion of the stone will be in this direction. But the stone does not fly off in that direction, does it? Because as long as the string is there, it will continue rotating So instead of flying off in this direction, the stone after a while, let's say, moves to some point over here. So obviously, because there is a continuous change in direction of the stone taking place, there has to be a force acting, and this force has to be acting along the string, because it is the string which is causing the force to causing the stone to change its direction at every instant. So as you can see, when the stone is over here, its tendency is to go in this direction, but it does not go in that direction if the string is present. It remains over here and then continues in its circular path. So there has to be a force which acts along the string, because it is because of the string that the stone is rotating in the circular path. Thus we can say that the direction of force on the stone is acting along the string. So as you can see, this is the direction of velocity, this is the direction of force on the stone. Now again look at the animation. We find that the rope is applying a pulling force on the stone, because of which it is changing its direction at every point of time. Now obviously when you look at the entire animation at once, it is impossible to understand it because the stone is rotating so fast. But as I demonstrated previously, it is because of the string that the stone is able to change its direction and not flying off. Because when the string is being cut, it is flying off in a tangential direction. So we can say that direction of force is towards the center of the circle, as I previously demonstrated to you. So now consider this diagram again. Over here, this is the direction of velocity or the direction of motion of the stone, and this, that is along the rope, is the direction of force acting on the stone. As you can clearly see, these two are directed at right angles to one another, or in other words, direction of force on stone and direction of velocity of stone are at right angles, or in other words, this is 90 degrees. So this particular force that is acting at right angles to the direction of velocity has a particular name to it. So over here we see that force is being exerted on the object, direction of force is towards the center of the circle, and direction of force on the stone and direction of velocity of stone are at right angles. This kind of force is known as centripetal force. Now centripetal force comes from two Latin terms. These Latin terms are centrum, meaning center, and peter, meaning to seek. So it means that center seeking force, or in other words centripetal force, which is nothing but a force which seeks out the center. As we clearly saw in the case of the string and the stone, the force was acting towards the center of the circle. Thus, we now define centripetal force. Centripetal force is a force which is directed towards the center of a circular path and always acts at right angles to the direction of motion along the circular path is known as centripetal force. Now again, in this definition, there are certain key aspects. The first key aspect is centripetal force is always directed towards the center of a circular path, as we previously saw, and it always acts at right angles to the direction of motion. So this is one key aspect and this is one key aspect, and in this circular path the force that acts is known as centripetal force. Now let us consider a very interesting scenario. Over you find that a car is being driven and it is taking a sharp left turn along a curved road. Now this road is curved in a circular manner. Over here you find that a mug which is placed on the left hand side of the car, after taking the turn, is sliding over to the right hand side. Now obviously, since nobody is pushing the mug from one end to the other, there must be some other kind of force which acts on the mug. So what is this force that is acting on the mug which is causing it to slide from one end to the other when the car is taking a sharp turn? This force is known as centrifugal force. Now, centrifugal force, just opposite to centripetal force, is a force that acts away from the center of the circular path. Centripetal force acts towards the center, centrifugal force acts away from the center. So now let us analyze the motion of the mug from one end to the other closely. Over here we have two views. One view is from inside the car, which I previously showed you, and the other view is a bird's eye view from the top of the car. Now in the bird's eye view, it is clear that the car is taking a sharp left turn along a circular path. Now let us consider what was happening when the car is traveling in a straight line path. From Newton's first law of motion, you know that whenever an object is in motion, it tends to stay in motion along the same direction unless and until there is an external force acting on it. So now consider when the car is driving in a straight line, the mug along with it is also moving in a straight line. Now what happens when the car makes a sudden turn? There is a certain amount of friction that is present in between the car tires and the road, and this friction provides the necessary centripetal force for the car to execute the turn, and this is why the car does not fly off in the outward direction. So the centripetal force provided by friction enables the car to make the turn. Now there is no centripetal force, or in other words, there is not enough friction between the mug and the dashboard of the car to provide centripetal force to the mug. So what happens? This car takes a sharp turn with the help of centripetal force, but the mug is still not able to make the turn because there is an absence of centripetal force. So the mug continues to move in a straight line. As I mentioned, due to Newton's first law of motion, it tends to go along in a straight line. So what happens, as you can clearly see, is the mug continues to move in a straight line, unlike the car, which has veered left. So it seems as if the car is sliding out from under the mug, or in other words, it seems as the car is moving out from under the mug. And this becomes apparent when we see that the mug is moving from one end of the car to the other. It is because there is an apparent force which makes us seem that the mug is actually moving from one end to the other, where actually what is happening is the mug is continuing its straight line of motion due to an absence of friction in between the dashboard and the mug bottom. So this is how centrifugal force acts. Centrifugal force is an apparent force. It is important to remember that centrifugal force is not a real force, but an apparent force which acts in a certain situation that a body appears to be acted upon by a force. So centrifugal force is an apparent force where it seems that this force is acting on a body while actually there is no force that is acting on the body. So this is centrifugal force. So we have studied what centripetal force is, a force which in circular motion acts towards the center of a circle, and centrifugal force, an apparent force that acts away from the center of the circle because it seems to be acting, but it is just an apparent force. So that sums up our discussion about centripetal force and centrifugal force.